In modern manufacturing, a component starts as a pristine mathematical model, but physically casting, machining, or molding that part immediately introduces variance. A theoretical digital design is entirely free of flaws. The physical reality of a manufactured object never is. Navigating the exact millimeter gap between the CAD file and the factory floor is where quality control succeeds or fails. Manual tools like calipers or micrometers work for simple linear blocks. They fail entirely when tasked with capturing the continuous, sweeping curves of an aerodynamic surface or complex mechanical linkages. To verify these non-linear designs, engineers have to extract millions of data points from the physical surface, translating a tangible object into a dense mathematical dataset. In high-stakes production environments, producing a component that looks correct to the naked eye is insufficient. Survival in precision manufacturing requires mathematically proving that the physical part matches its digital intent. The process of converting physical surfaces into high-density digital representations is known as 3D metrology. To execute this conversion and perform the required analysis, engineers rely on specialized software platforms like the PolyWorks Metrology Suite, specifically its latest iteration, 2024 IR 3.2. The operational workflow follows a strict path, ingesting raw spatial coordinates from the physical world, importing them into the software environment, and subjecting them to rigorous geometric evaluation. The ultimate objective of this software pipeline is to capture inevitable manufacturing deviations, isolate the deviations, quantify their exact magnitude, and formally document the results. A laser scanner captures a raw, chaotic cloud of coordinates. PolyWorks operates as the algorithmic engine that organizes those geometric points into actionable quality control intelligence. The inspection workflow begins by importing a raw point cloud, a massive collection of spatial data captured by a coordinate measuring machine or optical scanner. This raw dataset contains environmental noise. The first step removes these outlier points, leaving a clean, dense core of accurate data. Once isolated, the software algorithmically binds these points together, converting the loose coordinate field into a structured polygonal mesh. A scattered cloud of dots cannot be effectively measured for volume or continuous surface area. The polygonal mesh provides a solid, unbroken digital representation required for the software to calculate actual dimensions. Rigorous data preparation and noise reduction dictate the integrity of the entire pipeline. If the input data is flawed, the subsequent dimensional analysis will yield entirely inaccurate results. With the physical scan data correctly structured into a mesh, the software requires a baseline for comparison. The original digital CAD model serves as this perfect reference standard. The newly created polygonal model is introduced into the precise digital environment occupied by the CAD reference. PolyWorks then executes a part and CAD alignment protocol, calculating the spatial orientation of both models and locking them together on a shared X, Y, and Z coordinate axis. Establishing this shared coordinate system is a mandatory prerequisite for any analysis. It is impossible to calculate a precise geometric deviation if the two objects sit in slightly different digital spatial planes. This alignment serves as the absolute mathematical anchor for the inspection. Even a fractional misalignment at this stage produces invalid evaluation data later on. Once the physical scan and the CAD model are anchored together, the software runs a surface-to-surface comparison, calculating the exact distance between the two geometries at every single mapped point. This calculation generates a color deviation map. Looking at the map, green zones indicate perfect alignment within tolerance. Red patches highlight areas with excess physical material, while blue patches reveal gouges or deficits in the physical part. Engineers use this direct visual output to identify the specific locations and exact magnitudes of nonconformance without having to manually search through spreadsheets of coordinate data. The accuracy of this map relies on the operator correctly defining the specific inspection criteria and acceptable tolerance bands before initiating the comparison analysis. The color deviation map translates millions of abstract mathematical differences into immediate actionable insights, showing exactly where a die or mold needs physical adjustment. Checking outer surface contours provides a macroscopic view of the part, but it fails to verify complex internal geometries and tight mechanical interfaces. To evaluate deep internal features and complex spatial relationships, the process shifts to geometric dimensioning and tolerancing, or GD&T analysis. This diagram illustrates how the software verifies specific geometric traits. It assesses the exact perpendicularity of a shaft, the cylindricity of a drilled borehole, and the true location of mounting features. PolyWorks isolates these specific features from the scan data, computes their geometry, and outputs the exact numerical delta between the manufactured reality and the theoretical CAD requirement. Rigorous GD&T evaluation ensures that components will accurately interface with other parts and safely withstand operational stresses. The completion of the measurement workflow involves compiling the deviation maps and the GD&T calculations into standardized inspection reports. The software automatically formats this dashboard. The structured digital report provides the specific data tables and pass-fail metrics necessary for strict accountability and review. This entire data pipeline also serves a direct inverse function, reverse engineering. Inspection verifies a manufactured piece against an existing CAD model. Reverse engineering takes the clean polygonal mesh of a physical object and uses it to generate a brand new CAD file, typically for legacy components that have no digital blueprints. A captured point cloud possesses a dual utility. It provides the required math to prove the accuracy of current designs or the raw geometric material to digitally recreate old ones. As manufacturing integrates into the smart factory ecosystem of Industry 4.0, software platforms like PolyWorks feed directly into broader automated networks. The metrology data captured on the factory floor updates a digital twin, giving manufacturing systems the live feedback necessary to make automated, real-time tooling adjustments. The metrology pipeline increasingly utilizes rapid, autonomous robotic scanning and predictive analytics to detect and correct deviations the moment they appear on the assembly line. Pushing this constant stream of inspection data back into the network creates a continuous digital thread, linking the initial CAD design directly to the active production floor. Precision 3D metrology operates as the foundational intelligence, continuously ensuring that digital concepts successfully survive the transition into physical reality.